Okay, welcome back. So now I want to go over what you're not being told about why some people have glutathione deficiency and why they always get the flu. So this whole theme of what we're going into are some of the minutiae, but I think is all relevant from my perspective of why people have a far greater need, not just for glutathione, but for other things as we build on this case. So I'm building a case for you, but glutathione is dead center for what we're talking about here. And why does it vary from person to person? It's not just on nutrition, by the way. Let's get into it. What you're not being told about why some people are even more glutathione deficient, more prone to glutathione deficiency due to genomic predisposition. So I'm going into this aspect because I think it's very important. In my world, it's almost common knowledge. And I think it's common knowledge enough out there that you should know about it too, without feeling like, oh my gosh, I need to know my whole genome. No, I'm not saying that. I think you need to know a little bit about it. All right, I went into this pretty deeply on previous videos about epigenetics, not the human genome, but relevant parts of the human genome that you would want to look into. So why we need glutathione, how you can increase glutathione, and from autism to addiction to schizophrenia, that will be coming up again. You need to look into that for a deeper understanding. It's really pretty cool. So here's what we're going to look at. Oh, I've already scared you away. No, these are really important things to look at. This is what you call your methylation cycle, folate and methylation here, and what they call transsulfuration. Transsulfuration, this is just a big fancy word for saying glutathione factory. This is your glutathione factory. This is how you make glutathione, and no, you do not need to know every little step, but I want you to orientate to we have a personal difference between us. I don't mean you and me, but between each other, that we have various needs that are independent from our diet. And this is what I'm trying to drill into. It's fascinating, actually, and I hope you get hooked on it. So many people just can't create enough glutathione to meet personal needs. And they're vulnerable because of it. But that's just the way it is. They can address that if they know they are one of these people, okay? So let's look briefly. All these little blue boxes are enzymes, and enzymes that you can have working really well or really poorly depending on your genomic mutation. We call them SNPs, single nuclear polymorphism. It's a mutation. It's going to be either slowing it down or speeding it up, right? That's all you need to know. So all these little blue boxes are places that can either be working slowly or working quickly, and that's what we're looking at, the relevance, and they're not all equal. There's only a few of these, and now the list just got smaller, of ones that we look at. So there's MTHFR, we'll be talking about that, MTR, just a few of these. I'm not going to go into it now, but just think of all this as your glutathione factory. And not only do you have enzymes, right, that move this thing to the next stage, like an assembly line, right? But also, that's the enzyme. Each enzyme needs a certain little battery. We'll call it a cofactor. And those are nutrients. And so you can see these little small words here, and I'm not going to be emphasizing every little one. Serines and nutrient, glycine, B6, iron, all these little things, all these little batteries, if you will. I'm trying to give you an analogy. Battery that makes that enzyme work appropriately. If you don't have the cofactor, or if you have a bad mutation for that enzyme, something's going to get stuck. It can't stop completely, because if it stopped completely, you'd be dead. So obviously it's working, but it's going to work more slowly because of the nutrient. The cofactor is not there, and or the mutation, the form that you have, is just slow. Or if it's fast, it's throwing things out too quickly. Again, think of the assembly line. Things are being thrown out too quickly, and the next step can't make sense of it, and it's the problem for the next step. All right, that's pretty much all I want you to know. These are cofactors. These are, the blue boxes are enzymes, right? And so we're going to be looking at homocysteine as a word's going to come up again and again and again and again. Homocysteine to cystathione, cysteine. It is the tail end. All this is called your transsulfuration. These are all sulfur, 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 sulfur. And it goes in to make glutathione, which is a sulfur compound. And this is very important for your immune system, guarantee it. So it has to do with glutathione. It is the big product here, and a lot of other little products are being made along the way, but it's the big product in terms of human detoxification, in terms of energy production. You have to have that. So again, we're looking at that big circle. Methionine, where you get methionine from meat. That's your protein source. So if you're a meat eater, primarily fish, meat, chicken, poultry, whatever, you get plenty of methionine, but that's where it comes in. It's a dietary source. Methionine gets changed into homocysteine, and it goes around, and there's other fancy words like SAM, S-adenylmethionine. We'll hear about that. But I just want to say the three big bottlenecks that I'm most concerned of, that I look for initially, and we can get into the minutiae later, but the three big bottlenecks I want to pick out for you are ones that have to do with folate, the folate cycle, but folate in particular, choline, now we're talking about cofactors or nutrients, and B12, choline, B12, folate. Those are the three that I look for, that I test for. Are they up and running? Because most people will have a deficiency of one of these three, and that makes for a problem. Even if they have all the enzymes, all those little factory workers doing just the right thing, if they don't have the right thing to make that station work, it's a problem. So those are the three: folate, B12, choline. After that, you can look at B6, B2, B3. I don't want to get into too many pieces because there's a big common sense picture that we're going to here, which is, do you have enough glutathione? If you don't have enough glutathione, that's a problem. And we talked about that in previous videos. And homocysteine is going to help us understand if that's one of our problems. Methionine, homocysteine. This is the lab test we're going to look at later that anybody can get. This is a common lab test. It's not expensive. It's a big word, and you're not charged on a per word basis. It's a fairly cheap test for anybody in the public can get. We no longer have to go to your doctor. Ask your doctor for, I want my fasting homocysteine level. Do that. Or you can go get it yourself. Better yet, take responsibility for your own labs and know what they mean. So this is a lab test. This is going to tell us, do we have a problem here or not? When we talk about NAC, N-acetylcysteine, is a precursor for glutathione. That's right here, plugs in. That's pretty well known, and we've talked about that before coming up. Here's one of the things that I think is important to know, that homocysteine, which is a common lab that we're going to get into, increases as you get older. The question I want you to be asking for this whole thing, is it healthy that it's getting higher? And does it have to get higher? Or are we aging in a way that is not necessarily a healthy way of aging, and elevated levels of homocysteine is kind of telling us we're not as healthy as we could be, and maybe there's something we should do to bring that down? And the answer, of course, is yes. Here's the lab value. Conventional medicine says 11.4 is the cutoff. 11.4 is the cutoff, 0.4, not 0.5, not 0.3. And I basically use my sweet spot as around 6. But we're going to say 11.4. So if you use 11.4 as the level, what that shows is, and there's a lot of studies behind this, and here's one here saying, well, that means that the average male in the United States reaches that level when they're 65. The average female, woman in the United States, reaches that when they're 75. You go, well, yeah, that means their whole life they're in the healthy range, right? No, they're not in the healthy range. This is just very outdated information that is still used. This is the conventional level medical doctors use. This is the average woman's average level for women is age that hits 11.4, age 75. And here's the average level for men at age 65, 11.4. So when homocysteine level is over 14, listening in, when it's over 14, you double your risk for dementia. I just mentioned dementia. That's a whole nother set of videos I've done, but homocysteine is correlated plenty. It's not esoteric. It's not like, oh, a little secret. No, so over 40, we're gonna look at it. Anyway, so you see how it goes up by age, and this starts at age 12 to 15, so it's down around 7 at that. So it goes from 7 to 11.4 in about 40 years. You go, well, so what's the big deal? Well, it's something you can do and dramatically change the quality of health. You could also call it anti-aging. It's very much involved in anti-aging, but I'm not going to go into that. Double a risk of dementia due to homocysteine levels higher than 14. Covered a lot of that, 3 steps to reverse cognitive decline on this particular video. And we really go hard by saying homocysteine is implied with cognitive health. Or when it gets high, you go into what they call mild cognitive impairment, which is a half step towards dementia. And that's from homocysteine as a risk factor for dementia and Alzheimer's, 2002. So it's been out in New England Journal of Medicine. It doesn't get any more conservative than that. So I'm going to break it down. There's a few little subcategories, but I want you to say that it's for pretty much all ethnicities. It varies a little bit. So non-Hispanic whites, this is their pattern, slightly different. Males are higher than females regardless. The risk of dementia is 14, conventional medicine line here. The ideal range is right down at the bottom. And you say, well, that's according to conventional medicine, that's just a 12 to 15-year-old. No, it could be all of us. Homocysteine levels and age for other ethnicities for comparison. Non-Hispanic whites, that's what I just showed you. There you go, 11.4. This purple is the 11.4 range, the 11.4 range in all three. And this is non-Hispanic blacks, Mexicans, which are a nice mix of, everybody's a nice mix, right? Of actually, the Mexican population is Amerindian, which is primarily Mayan, and blacks from just like the United States from the slavery days, and Hispanic, Spanish. So you can see the pattern is consistent, right? And men are always higher than women, and that's 1999. Okay, high homocysteine is most definitely a serious problem. The importance of homocysteine lies in the potential prediction of cardiovascular risk in COVID-19 patients. So what I'm saying here, you can substitute COVID-19 for the flu. You could substitute it, this is the flu season I'm focusing on. It's a viral respiratory infection is really what COVID-19 is. It has its special aspects, but here it says, besides being cardiovascular, which means atherosclerosis, cardiovascular diseases, heart attack, and stroke, this is pretty well known if you're in the medical field, but homocysteine now over 15, they're saying is a problem. So now you're getting 14, 15, we'll even get a 16 one. Just say it's a problem. I wouldn't get too stuck on the number. So homocysteinemia, which means chronically elevated homocysteine in the blood, as a risk factor for potential nutraceutical targets, meaning, of course, where we get most of our research is through pharmaceutical companies. They're doing the research to find the reality, which we enjoy, and they want to make a pharmaceutical that's going to certainly make everything better. But what I want you to see here is that homocysteine is related to reproductive apparatus, they say here, menopause, sexual dysfunction, pregnancy, sensory, your ability to hear, nervous system, epilepsy, dementia, Alzheimer's, and Parkinson's. Kind of already covered that. Kidneys, excretory apparatus, and basically bone health, and certainly diabetes, which is your pancreas. There you go. Homocysteine, cardiovascular, diabetes, neurological osteoporosis. You know it's important, and that's an Italian study, 2019. So this is not old news. This is really going deeper now. By measuring homocysteine, HYC, it's homocysteine, can identify patients who are at higher risk for severe COVID infections. So hyperhomocysteinemia is related to many viral infection outcomes, including human hepatitis, human papillomavirus, and HIV, and you can go on further. The relationship between the prevalence of genetic polymorphisms. Now we're going to get into one of those things. Remember I talked about MTHFR? So the MTHFR C677T, which is particular allele, we'll get into that, and COVID incidence needs to be assessed. This is from this study down here, predicting COVID hospitalized patients' outcome strictly on homocysteine. Strictly on homocysteine. We talked about glutathione before in the last videos. Now we're talking about homocysteine. If it's up, they're going to get a bad outcome. That's what they're saying here. And now they're saying, wait a minute, within that category, there's people that have certain mutations that are more vulnerable than everybody else. B vitamins, B2, B3, B6 have a key role in the enhancement of the immune system, right? Think of that particular slide that I showed you. Homocysteine has been proven as a critical biomarker of cardiovascular risk and complications of COVID. Homocysteine can identify patients at higher risk for severe COVID infections and is easily determined by a simple and affordable laboratory test, which is kind of my pitch to you. Get your labs done, especially if we're going through flu season, but you should have a running understanding of homocysteine in your life. Don't go, oh, I don't see my doctor, I don't have a doctor. You don't need a doctor. You can go get your own labs. On the back of every video I do, the description area is a place that you can get your own blood work done, and I don't get anything out of it, so I'm not attached to it, but go do it. I'm attached to the message, which is go do it. All right, so predicting COVID patients' hospitalized outcomes on homocysteine. The association between homocysteine levels over 16, right? We did 14 and 15 and over 16, and worse COVID prognosis is well known. South Africa, so that's from South Africa. We're going around the world. Remember, this whole thing was all this information that's coming out of the pandemic we had from COVID for the last 3 years is remarkable. And it's not like the information we're getting primarily in the United States. It comes from a different perspective, and it's a non-pharmaceutical perspective. From name the country, the questions they're trying to answer is, how can we take care of this now? You know, to say that, oh, there's a comorbidity of diabetes and obesity, it's not helpful. They're in the hospital, they're in ER, they're in the critical care. What are you going to do now? This is what we're going to. What do we do now to change that situation? For one, they don't die, and they have fewer and fewer systems so they can be discharged. This is what we're after, and this is where all these other countries are coming from. Well, comorbidities, okay, we'll take care of that later. That's like a year to 10-year population change. We're talking about how do we treat them in the hospital. All right, so what they're saying is your Homocysteine level will determine how well you survive this season, this flu season, from stage 1 passing to prolonged acute to 3 long COVID-like for needing hospitalization. Homocysteine is a marker for predicting viral disease severity. 2022, and that's a Turkish study. Are you getting this now? It's funny how I'm not, if there were American studies from the US, I would point to it and say, hey, here you go, but they're not there. These are from countries that need to improve their situations immediately, as soon as possible. And therefore, they're looking at all the data they've had on all these people to say, we need to sift through and find out what's relevant, what's treatable, and let's move. Okay, I'm going to show you about homocysteines. Okay, so now we're looking at a panel. This is all the labs that I take, and I sort of squished them all down and did some sort of summary levels to compare. So what I did, first thing I want you to know is every yellow bar is homocysteine. So it's repeated. So I don't have to, so it's easier to compare to the levels just above it, right? So I have homocysteine. The lowest is over here. So according to Dr. Carl, the ideal level, as I say, is around 6. So this is really around the ideal level. And that's why I put a blue bar there. And these are actual numbers of actual people. And so this is way out here at 18, clearly high. We've had higher as well, but I just pulled these together, threw them together, and I sorted from low to high solely based on homocysteine. So low to high, every yellow bar, low to high, same numbers, right? All the yellow bars are all the same. But now I want to compare it. How does homocysteine compare to, let's say, total cholesterol? Is there any correlation? And we sort of eyeball that. And we say, yeah, not too much, not too much. How is it relative to HDL or triglycerides? I'm going to skip all those because that's not where I want to look at. But let's compare homocysteine compared to insulin resistance. Now that's interesting. And what all the red dots, those are the red dots, the red numbers are the numbers that are clearly out of range, even by my level. They're way out of range. So they're very excessive. So what you can do is you can just eyeball where most of the red is. And so when we're looking at insulin resistance relative to homocysteine, as your homocysteine goes up, you can see there's more insulin resistance there. Down at this level, yeah, there was some exceptions. You figure some of these people are on medications, and so it kind of changes their labs. It's not just a perfectly normal. But I would say, in my view, when we look at insulin resistance, which we measure by triglycerides over total cholesterol, insulin resistance, which is another formula I do, a log, doesn't matter. And a third way is simply a formula of insulin versus fasting glucose, and you go get that number. And so these are the normal ranges, anything over 1.5 for triglycerides over HDL cholesterol, HOMA-IR, which is 0.5, 1.4. So anything over those numbers there would get a red mark. And so now we see that there's a lot of red over here. Or let's compare it homocysteine. Down here we go, like homocysteine relative to glucose. Now there seems to be a pretty good comparison. We have 103 here, and I put that in red. It technically shouldn't be in red. And so it's fairly low. Let's go down here. We're seeing, 179, definitely 201, 104, 113. So somewhat of a correlation. When we look at insulin resistance, which is, insulin right here. Insulin is definitely higher with higher homocysteine. Now let's just jump down and go to omega-3s, right? So that's your omega-3, omega-6 ratio and also total omega-3. So this is your omega-3 index, which means your total omega-3 fatty acids, which are your EPA and your DHA, okay? So there's that. So let's just look at that. Homocysteine relative to omega-3. Well, we find the lowest homocysteine does correlate with the highest omega-3. That's a pretty tight correlation. Whereas the highest homocysteine has to do with the lowest EPA, right? Omega-3. That's interesting. That's a very tight correlation. And that's also known in the literature, by the way. Also factors about dementia and so on. Now let's look at the ratio. You could say it's pretty much the same thing, but now we're throwing in omega-6. So the highest ratio, which is the worst, right? You want a 1-to-1, 3-to-1, 1-to-1, ideally 1-to-1 ratio. We don't get that for any of these people. But the ratio is generally lower over here. It's actually fairly low in the middle as well. But so a tight correlation with omega-3, and then we go, your risk factor for heart problems is what this word is down here. So there you go, we have some correlations. Let's now compare homocysteine, I'll shoot this up, to inflammation. High homocysteine, high inflammation, low homocysteine, lower. It's not completely black and white, but it's pretty close. What about with vitamin D? So now we have homocysteine with vitamin D. Well, we have, we have some pretty poor results, don't we? High homocysteine with very low vitamin D. I would say that's a pretty tight correlation. And low homocysteine, which is a good thing. Remember, Carl's numbers over here, Dr. Carl's numbers over here. We have better numbers for vitamin D. And then we can look at, we'll leave it at that, but and these are just other deficiencies we look at in a whole different way. That's homocysteine. Okay, so now that you've seen homocysteine both in reality, what actual people walk in with, and what some of the documentation in the studies and so on and so forth, let's put this into some correlations with other things. Let's build on this a little bit. We already talked about glutathione, and speaking of which, you remember this from last video, this is the ratio of reduced glutathione versus non-reduced glutathione, oxidized glutathione. What you want is a lot of this. That's a degree of health. Higher levels of reduced glutathione is what everybody wants. That's your big antioxidant. We've talked about that. So GSH is reduced glutathione. We want a lot of it. Well, the problem is it decreases with life. It decreases with age. So here we are at 0 supposedly, but you can see how it drops. And here's the correlation, which is pretty remarkable. Nothing correlates in life like that. And so what we're seeing is by age 80, you are at, I shouldn't have covered that up, but that was roughly 25, probably 25 in there. But we can see the ratio changes. And here we have relative to 20, we're down about half. So this is reality. I want to show you. The reality is glutathione decreases with age. We know that. It's been very well documented for the last probably 30 years. This is from Tufts in 2013. So they're using cysteine. Remember, cysteine's a precursor for glutathione. Cysteine in the red blood cells as a function of human age. So now they're saying this is it. As a function of human age, we can measure cysteine, glutathione, and we can tell you how old you are. So it's part of anti-aging, if you will. Correlation with reduced glutathione and total antioxidant potential. Right? The lower your glutathione, the less your antioxidant ability. So we just said that homocysteine is increasing through life and glutathione is decreasing through life. And we sort of drew over saying, all right, here's that same level, right? At 65, an average man is 11 in the United States, hits 11.4. And we go over here, we say, that's how low he has maybe nearly 0 glutathione, not much more than 0 glutathione, and he has high homocysteine. It sounds like that guy's in problem, is going to have a problem, or the average male in the United States is going to have a problem. We're all going to go dementia. But there's ways to change that. So what I'm showing is there's a foundation here of understanding of things we can address. And this comes from that same study from Tufts. Okay, and women, the same thing. Women are marginally better off, if you will, because they're a little slower to get lower in glutathione and a little slower to get high in homocysteine. Okay, again, these bottlenecks we talked about, genomic predisposition, problematic SNPs, single nuclear polymorphisms, right? That mutation we're talking about. And these are a list of substrates, if you will. MTHFR, it requires B12. We'll get into that in a second. But the 3 genomic bottlenecks that I look for, MTHFR, MTRR, showed you that before, and CBS, which is cystathione beta synthase, who cares, but it converts homocysteine down to glutathione. If this is, right, we're seeing this is increasing in life, right? This is increasing as we get older, and this is decreasing as we get older. It got doubly bad, didn't it? All right, methylation cycle, detoxification, cellular adaptability. It turns genes on and off, helps turn genes on and off as the per needs basis, and gene regulation. All right, methyl donors, again, are folate, B12, these what they call methyl donors. We're going to talk about these specifically. Folate, B12, SAM, S-adenomethionine, choline, and trimethylglycine, otherwise known as beta-ene. Methyl donors are a reference that you need to know about. Trimethylglycine, beta-ene, choline, B12, folate, and SAMe. As we get older, we have too much homocysteine, and we have too little of glutathione. This is our issue we're trying to address. By having too little glutathione, we are going to be too vulnerable to viral respiratory infections, and really viruses of a lot of types. There are only 3 possible reasons why this can happen. Having both elevated homocysteine and glutathione deficiency at the same time as we get older. Nutrient cofactors, nutritional deficiencies. We have particular mutations, SNPs, that result in poorly functioning enzymes. Or we have a combination, and that's usually, all of us have a combination. Here's how really important these are. So, enter the work of Dr. Randy Jerde at Duke University, 23 and 27. He did the simplest experiment that shattered the world of research, absolutely. And since then, it's probably been done 1,000 times. But here's what he did. He got what they call the agouti mouse. This is a mouse that is bred, right? You've heard about knockout mice and so on. So this is a agouti mouse. It's kind of a knockout mice. It's meant to be disease prone, but specifically it's meant to be this. An agouti mouse is genetically designed to be large, obese, kind of saying the same thing, diabetic, yellow, and highly prone to cancer. So obese, diabetic, yellow, and highly prone to cancer. So what he did was this. He gave them both mouse chow. And by the way, there is a really specific formula for mouse chow. He gave them both mouse chow. And then to this one, he added those methyl factors, methylation factors, the B12, the folate, the SAMe, choline, trimethylglycine, betaine. He added this. So they're both doing mouse chow, and he just added in some specific vitamins, if you will, specific nutrients. So here's what he did, right? He added in folate, B12, choline, trimethylglycine, and SAMe. Remember that? He added those in. That's the only thing he did different for this. So they're vital, right? They're pretty important, big players. Remember we said how folate, B12, and choline were like the biggest players? They absolutely are. The others are big too. All right, so I went from large, obese, diabetic, yellow mouse prone to cancer, the agouti mouse, pretty picture, huh? To a normal, brown, healthy mouse. Healthy, normal mouse. He just gave him 4 other nutrients, or was it 5? 5 other nutrients. Gave him the methyl factors, methylation factors. So technically, this is called a pseudo-agouti mouse because it was bred to be an agouti mouse. They gave it mouse chow and those methylation factors, and it became healthy. How could he do that? How could he reverse the way the mouse was bred to be, generation after generation after generation after generation? Did he ask for his money back? Just the methylation pattern changed. It's because the DNA didn't change, right? There's no genetic underpinning to change, but the methylation pattern changed. They turned off some genes and turned off others. So when you methylate, you turn genes off. I did a number of videos all about this because it's very fascinating as why this mouse will change your family's health for generations. And there you go, and I'll put the link above, of course, as well. All right, another way to look at this is what I call traffic circles. You have the methylation. These two together are called methylation. So the methionine, homocysteine traffic circle. Methionine changes to homocysteine. Homocysteine goes down to glutathione. Remember that through the transsulfuration. Big words, but they're there. Don't get stuck on it. And you have the folate acid cycle, the traffic circle. And there's the MTHFR. That's where it's one of the famous mutations, if you will. And biopterins are really about turning neurotransmitters on and off, but they're all interrelated. Traffic circle, traffic circle, traffic circle, traffic circle to glutathione. All in all, it's all your glutathione factory. Okay, here's another way. How do we know about people's enzymes? How do we know about their mutations? Where do we go for this? Well, this is now sort of pulled from and made anonymous, of course. I think this is probably 6 or 7 years old. It's changed since then. But here we have a male, 50, 80 pounds overweight, diabetic, alcohol issues, 12 children, family history of diabetes and addiction in preceding generations from him, genomic predisposition. So he had MTHFR. There's 2 forms of this we're concerned about. He had the worst forms, which is the same form that I have and my wife has. And then there's the MTRR. I've told you about that. He has that, there's 2 forms. He has the worst form of that. So he's homozygous, and he's heterozygous for the CBS, cystathione beta synthase. Remember that one I showed you? So the causes of hyperhomocysteinemia, elevated homocysteine in the blood, major cause is the genetic defects of the transcription of enzymes responsible for the homocysteine metabolism. In other words, those little chunks, those little pieces weren't working correctly, and the homocysteine got backed up. It couldn't be made back into methionine, and it couldn't go down to be made into glutathione. It was stuck, and it just got to be bigger and bigger and bigger. Okay, in particular, the polymorphisms of the main enzymes involved in this that we're concerned about of homocysteine metabolism are MTHFR, methyl tetrahydrofolate reductase, CBS, cystathione beta synthase, methionine synthase, methionine synthetase reductase. But primarily the most notorious and most of the stories are around MTHFR. But we look at the context. We try not to say it's just one thing. You got this one problem. It's usually you have a few problems. So one of the most studied polymorphisms is the MTHFR C677T on the encoding for the folate metabolizing enzyme MTHFR, which I showed you. 10% of the world's population is homozygous for C677T polymorphisms. I'm part of that 10%. My wife is part of that 10%, and the frequency can rise up to 26% in southern Italy and 32% in some areas in Mexico. There's a close relationship between MTHFR polymorphisms and folate levels in the serum of pregnant mothers specifically. Okay, again, we're looking at genomic predispositions, problematic SNPs, remember? The MTHFR, the MTRR, the CBS. And so the guy that we're looking at is check, check, Check. Homozygous, homozygous, and heterozygous on this one. 3 bottlenecks. Because this increases as we get older, that decreases. We have to address the bottlenecks. The glutathione factory has a few snafus that we can and will address. All right, so remember the nutritional deficiencies that had directly affected his ability to create glutathione? And they were glutathione, cysteine, serine, and glutamine. So when we look at, this is a whole nother panel of intracellular testing, but this is how we get a picture of, yep, makes perfect sense. He's deficient, he's deficient. So this means just on the nutrient side, forget about the enzymes that we just looked at. On the nutrient side, he can improve things. And the takeaway here is if you have some of these mutations like I have, it just means you have a higher need. It doesn't mean there's, oh my gosh, I have this big problem. You have an elevated need, a higher need. You got to take a little more than other people. You got to be a little more aware of the food you're eating and or supplement specifically, but don't over supplement. You just need to do a little more. Over supplementing is also another curse of our culture right now, but just enough. But wait, there's more. I'm going to end with this for what I'm going to be covering next time. There's another group with glutathione deficiency concern. These are people with a G6PD deficiency, but they are a lot more their story than they are the canary in the coal mine, for sure. But their story, their predisposition really speaks to how we are. We're all become more like them. But we're going to go into that story next time. Till then. So if this is something that you're interested in, that is a topic that I obviously go deeper in terms of labs, in terms of how to do it, in terms of why you would want to do it, various topics, as you've seen that I've done in the past, then please let me know below in a comment. Till then.